All right, it is 9 a.m. Welcome to Advanced Kentucky's first online content review session for AP Calculus AB. I'm Aaron Timmons. I'm the Mathematics Content Director for Advanced Kentucky, and I'm joined with my co-host Michael Marshall, who is the Content Manager for our Access to Algebra program, as well as our presenter for today, Melanie Gray from Madison Central High School. We've got a few meeting etiquette slides to go through, and then we will get started right away. So if you're looking at the screen I'm sharing, please make sure you've got the handouts for today. They can be accessed via that link or via the KYAP 2020 website. Melanie's contact information is right there, but we will be recording this video, or we are recording this video, and it will be posted for on-demand viewing at your convenience. So host information, if you need to reach out to us, to email us, to follow us on Twitter, look for us on Facebook. All of that information is there. Again, you can go back and take a look at that when you need to. Today, your microphones will be muted. They'll be muted the entire time. Your videos will also be disabled, or I will make sure they're disabled. So please make sure you're utilizing the chat feature. At the bottom of your Zoom screen, you can click the chat button and the chat box will pop up. Please make sure you are asking any questions to us through that chat box. Michael and I will be moderating, and we will be asking questions to Melanie that you all have. So please make sure. We want this to be as interactive as possible. So any question, no matter how large, how small, meaningless, meaningful you think they might be, feel free to ask them. And between all of us here, we will get you a satisfying answer. So I also encourage you to check out the KYAP 2020 website for additional information besides the events. There's resources for teachers, resources for students. You can also find information for all other AP content review sessions that are going on during the month of April. So we hope that you can help find some stuff right there. All right. So without further ado, I'm going to stop sharing my screen. And I will turn it over to Melanie, who will be taking us through the first of our 4 content review sessions for calculus. So Melanie, take it away.
Hey everyone, I'm just going to share my screen really quickly and go over the agenda for today. You'll bear with me here. So as Aaron said, this is content review session 1. We're going to be talking about integration and the accumulation of change. I am Melanie Gray. I teach at Madison Central. This is my 19th year. I also adjunct for EKU, so just to let you know a little bit about myself. A preview of the next 4 weeks, just so you kind of know what's coming up. Next week, we'll have Mr. Brock Strickland presenting on the fundamental theorem of calculus, and then I'll be back with you on the 20th for differential equations, and then Mr. Strickland will be back on the 27th for free response strategies. And so for today, we have already sort of gone over the introduction and the overview. We're going to start out reviewing Riemann and trapezoidal sums. So the first part of this will be more instruction for those students who didn't get the chance to learn about Riemann and trapezoidal sums, or maybe those that it's been a while and you just need some reminder. And then we'll wrap up the session today with looking at some more recent free response questions that deal specifically with Riemann sums and trapezoidal sums. All right, so I'm gonna, if you were able to print off the handouts from the website, I'm gonna start by looking at the Skill Builder 6.2. So if you have those notes handy, you can go ahead and be getting those out. Then if not, then of course, any students out there, you should have pencil paper, be taking some notes, and then you can always go back and print out the handouts after the fact. So I'm going to do a new share. And so now you should be seeing Builder 6.2. And I first want to just give credit to Mr. Tony Record. He's the one that created this handout, and so I wanted to give credit to him. He gave me permission to use this. And so this is our piece that we're going to use for instruction today. Notice that in example 1, we have the function f of x, and it's on the interval 0 to 4. We're being asked to find approximations of the area lying between f of x and the x-axis, x equals 0 and x equals 4. So we're going to start with doing a right Riemann sum and then a left Riemann sum, and then we'll go look at a few of the free response items, and then we'll come back and talk about the trapezoidal sum. So we know that when we are approximating the area under the curve, we're actually approximating a definite integral. And so for this particular function here and graph, what we're going to do is we're going to approximate the integral. We're going to approximate the integral from 0 to 4. So those are my bounds, since those are my x bounds, and the function is the function f of x that was given in the problem. And so that's what we're approximating when we approximate the area under that curve, or the area between the curve and the x-axis. And if we're using a right Riemann sum, we're going to come from the right bound of 4 and use that height to build our first rectangle. And you can see here that the first rectangle has a height of 0. So of course the area is going to be 0 there. Then we're going to come over to 3 and we're going to build our next rectangle to have a height when x equals 3, that y value there will give us the height. And then when x equals 2, we're going to go up until we touch that curve, and we're going to build our rectangle. And then for the last one, we're going to start at x equals 1, go up, up, up until you touch the curve, and then you're going to build your rectangle. All right, so now we know that the area of a rectangle can be found by doing base times height. So to approximate that area under the curve, we're going to do base times height plus base times height plus base times height plus base times height. So all 4 of those rectangles, find the area, add it together, and that's going to give us our approximation. Remember that n is the number of subintervals, so you can think about that as the number of rectangles. And so I'm just going to write here as a reminder that our area, we're using base times height because we're using rectangles. And so we're going to add all those together, starting with a base of 1 and a height of 0 for the red rectangle. Now, the base on each of these rectangles are going to be 1 because it asked us to give 4 subintervals, and since we were going from 0 to 4, I knew that my base was going to be 1. When we get into talking about some of the table problems, your base of your rectangle is not always going to be the same, but for this example it is. Then I'm going to add on to that the base of the green rectangle times the height. Now the height of that rectangle is going to be determined by the y value x equals 3. This value here, the height of the green rectangle, is going to be f of 3. So remember, to find f of 3, we simply substitute into the formula for or substitute into the function f of x. So -1/2 times 3 squared plus 8 will give us the height of that rectangle. Then we're moving on to our purple rectangle here, which also has a base of 1. Some people like to just factor out that base of 1 to the front. That would be okay too. But I'm going to substitute into for the function. So f of 2 will give me the height of my purple rectangle. So it's going to look like -1/2 times 2 squared plus 8. And then finally, for my last rectangle, the base is again 1. And the height here is going to be my y value when x equals 1. We'll call that f of 1. And so we have -1/2 times 1 squared plus 8. Now I'm also going to take this opportunity to show you with your calculator how you can type this in a little bit easier. If this were a calculator problem, you could type all that mess in if you want to, but I'm going to share my screen with you and show you sort of an easier way to deal with the calculator here. And if you're not aware, Texas Instruments has given the TI SmartView software for all of teachers and students a trial version. And so that's what I'm using here. It's a really nice version to use. You can use that at home. Laptop, whatever, you can download that. All right, so what I'm going to do is I'm going to go to y equals, and I'm going to type in my function into y equals. So I'm going to type in -1/2 or -0.5 x squared plus 8. Oops, I didn't come out of my exponent, I'm sorry. So -0.5 x squared plus 8. And then I'm going to go back to my home screen. And since I have that function stored, then I can do alpha trace and snag that number 1, the y sub 1, where my function is stored. And I'm going to evaluate that at 3. So technically, if I'm typing it all in, I would be doing the 1 times 0 plus 1 times y sub 1 of 3. So it will just calculate that function at 3 that we have stored into y sub 1. And so then I'm going to add to that 1 times alpha trace number 1 is where I'm snagging that y sub 1. I'm sure there's other places that you could find that. That's where I like to go. Let's see, the other one was 2. So y sub 1 of 2 plus now, obviously I wouldn't be putting in excuse me, these 1 times y sub 1, but I just want to make sure you see where all this is coming from. Okay, and then I think that's my last one there. Oh, I did 1 times 1 back there, didn't I? It should be 1 times 0. So I made a mistake here and put 1 times 1 instead of 1 times 0 when I was trying to show you the whole line typed in. So I can go up and highlight what I just typed in and hit enter, and it brings it back down. It just copies it down. And so I can go back to the beginning and fix my mistake. There we go. So now I got 17 for that approximation. So I'm going to go back to my other screen here. So that's going to give me an approximation of 17 with a right Riemann sum. Now let's go ahead and look at the left Riemann sum, which is very similar, except we're going to start at the left endpoint. So when I'm talking about endpoints, we're on the interval 0 to 4. So with the right Riemann sum, I started over here at 4 to build my rectangles. And now I'm going to start on the left-hand side for my left Riemann sum. So let's start here at 0. And the height of my first rectangle is going to be the y value when x equals 0. Then for my second rectangle, I'm going to start at 1 and I'm going to go up until I run into that curve. And that's going to be the height of my second rectangle. And then we're going to do it again when x equals 2. That y value is going to give you your third rectangle. And finally, your fourth rectangle will be a height when x equals 3. So we'll do this one a little bit faster by using some of our notation. So we're still approximating the area under the curve from 0 to 4 of f of x. We're using a left Riemann sum this time. So our base is still 1, but our height for the leftmost rectangle is going to be f of 0. So this height here is the y value when x equals 0. Then we're going to add to that a base of 1 times the height of the purple rectangle, which is going to be f of 1. Then we'll add to that the base of 1 again, times the height of the green rectangle, which is f of 2. And finally, the fourth rectangle is going to be a base of 1 and a height of f of 3. And so for sake of time, I'll go ahead and give you guys the answer for the left Riemann sum. It should be 25. And so as you can see on these two answers, if you compare the left Riemann sum to the right Riemann sum, it looks like your left Riemann sum is going to be an overestimate and the right Riemann sum is going to be an underestimate. And that's not always the case. It all depends on whether the function is increasing or whether the function is decreasing. So it looks like this function is decreasing. So now for those of you that printed out your handouts, if you look at the other file that we posted, it looks like this, integration and accumulation of change. If you'll look at the first page in that file, it's the justification page. We'll go ahead and fill in this little table, which can be helpful when you're writing justifications for free response items.
And Melanie, I'm going to interrupt for just 1 second. We've got a lot of people joined us since we started. So just a refresher, these handouts can all be found on the KYAP 2020 website under the event details for the specific session. There's also a link I'll put in the chat box. You may or may not be able to use the link, but you can write it down. It's a bit.ly link. And then also, I guess we went over introductions really fast, but if everybody in here would like to type in their name and where they're from, what school they're going, they're attending from, that would be great.
Awesome. All right, so as I was saying, if you had a chance to print off those handouts already, then great. You should be looking at that second handout, looking at the justifications. But if not, then certainly you could just jot this down on your own paper, and then when you get a chance, you can go back and print those off when you get a chance. So we just looked at an example of a left Riemann sum and a right Riemann sum, and our function was decreasing. And so when our function was decreasing, the left Riemann sum was actually an overestimate. So I want you to come down here, for those of you that have the handouts, and I want you to write that a left Riemann sum is an overestimate of the area when f of x is decreasing. And then if you look down under the right Riemann sums, we say that a right Riemann sum is an underestimate when f of x is decreasing. So in both of those cases, because it was the same function, we had a decreasing function. So what you're going to use this for is whenever you are answering a free response item, if the free response item has to do with left or right Riemann sum, then sometimes they will ask you if the estimate is an overestimate or if it's an underestimate, and then you have to justify that. So you would justify that with this sentence. You would say, just as I've said here, that the estimate is an overestimate of the area, and the reason is because f of x is decreasing. We can also go ahead and fill in these other two blanks. So if the overestimate is when f of x is decreasing, then the underestimate comes when f of x is increasing. So if your function is increasing, then it switches. The left Riemann sum turns out to be an underestimate, and the right Riemann sum is an overestimate. And I apologize if that writing is underneath the picture of me. Just let me know if you can't see what I'm writing. So here I'm going to write f of x is increasing. Okay, so let's take a minute and let's look at a free response item. Dealing with the left Riemann sum. So this is in the same packet as the justifications, and this is from the 2017 AP Calculus AB free response item. And we're going to look at numbers 1A and 1B, and then we'll go back and we'll look at the midpoint example and then also the trapezoidal rule. So this free response item says the tank has a height of 10 feet. The area of the horizontal cross section of the tank at height h feet is given by the function a, where a of h is measured in square feet. The function a is continuous and decreases as h increases. Selected values of a of h are given in the table above. So part A says use a left Riemann sum with 3 subintervals indicated by the data in the table to approximate the volume of the tank. Indicate units of measure. Now, for you to understand how we get the volume out of integrating, A of H may be a little beyond the scope of what they're asking this year. On the AP exam, we know that you're not being tested over Unit 8, but I do believe that it's a possibility that you would see a similar problem to this, but just asking you to approximate the area under the curve. So we're going to go ahead and we're going to write that we have the definite integral. It's asking us for 0 to 10 as far as the height is concerned. So we're using our h values for our bounds. And then we're integrating a sub h dh. And so we're going to do that by a left Riemann sum. And notice that we have a table here, and a lot of the Riemann sum problems or trapezoidal sum problems that you will see on the AP exam will come from tables. So the way that this works is if it's a left Riemann sum, you're going to start on the left-hand side, and the difference between your x, or in this case, h values, that's going to give you the base of the first rectangle. So between 0 and 2, we have a base of 2 for that rectangle, and the height is going to be 50.3. Now, like I said, this is a left Riemann sum, so I'm starting on the left-hand side. If this were a right Riemann sum, we would start on the right-hand side of the table. So for my first rectangle, I'm going to do base times height of 50.3. Then I'm going to add to that my next rectangle, which has a base of 3 since we're going from 2 to 5. And the height is going to be 14.4. Then finally, we're going to add to that a base of 5 and a height of 6.5. Now notice I did not use the value of 2.9. So for a left Riemann sum, you're not going to use the rightmost y value. And if you're dealing with a right Riemann sum, you're not going to use the leftmost y value. All right, so for a free response item, once you make it to this point, we haven't indicated units of measure yet, but once you make it to this point, you do not have to simplify further. Once you have a numerical answer, you can get full credit here. If you do go ahead and simplify or punch it in your calculator, because this is a calculator problem, remember on past exams, if you're looking at number 1, 2, your calculate active, and then 3 through 6 were non-calculator problems. So if we do punch that in our calculator, we get 176.3, and that would be measured in feet cubed. Now, as far as the scoring is concerned on number 1A, it looks like 2 points were awarded this particular year. You got a point for the left Riemann sum and then a point for the approximation. But this here, like I said, would count for both of those points. You wouldn't have to actually multiply and add it to get your second point. Now that it did ask for units of measure, and this particular year you had to do units of measure on, I believe, A, B, and C parts. So if you got the correct units of measure on all 3 of those parts, then you earned an additional point. So you didn't get a point just for this particular unit, but if you got the correct units on B, A, B, and C, you got another point. And then for part B, it says, does the approximation in part A overestimate or underestimate the volume of the tank, and explain your reasoning. So this is where our little justification sheet will come in handy. So we look at the function to see if the function is increasing or if it's increasing. There's 2 ways that you can do that. First of all, it tells us in the problem that our function A is decreasing. If you look right here, the function A is continuous and it decreases. So it tells us a decreasing function. If it doesn't explicitly tell you that it's a decreasing function, you can always look at your y values, and you see how we started with 50.3 and the y values are getting smaller. That would also tell you it's a decreasing function. So since my function is a decreasing function and we were using a left Riemann, then I know this is an overestimate. So I'm going to write down the approximation is an overestimate since A of H is decreasing. Another thing I want to point out is you want to make sure that you are using function names. So notice that up here in part A, I'm showing the integral of A of H dH. Make sure that you're specific to the function name, that you don't want to use f of x if f of x is not in the problem. Of course, we don't want to say, we don't want to use pronouns or say the approximation is an overestimate since it is decreasing. You want to make sure that you specifically state the function name here. All right, let's go back to our skill builder and let's look at the midpoint sum and then the trapezoidal sum. While I'm doing that, let's just see if there are any questions. You want to give me a thumbs up in the chat box, or if you have a question, if you want to type that in the chat box for me while I'm pulling this other question up here. Big shout out to, I see Morgan County Model Lab, Knott County Central. Just want to take a minute to shout out to some of my schools I see in the chat box. Great to have you all with us today. All right, let's look back at this midpoint example. So for the midpoint example, we have n equals 2, which is different. Our subintervals has changed. So now they're asking us to use 2 rectangles to approximate this. And since we're still going from 0 to 4, to do a midpoint, what you're going to do is you're going to divide it up from 0 to 2 and then from 2 to 4. And the height of your first rectangle is going to be halfway between 0 to 2, which is, of course, 1. So you're going to start here at 1, and you're going to go up, 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 up until you run into that curve. And then you're going to build your rectangle the height of that curve when x equals 1. Then for your second rectangle, we're going to start at 3 because 3 is the midpoint between 2 and 4. And I'm just going up, up, up until I touch that curve. When x equals 3, grab that y value, and that's the height of my next rectangle. So I only have 2 rectangles this time because I have 2 subintervals. So we are still approximating the area under the curve, or the definite integral from 0 to 4. Our function is still f of x. And so for our first rectangle, our base this time is going to be 2. So notice here that the base has changed to 2. And then the height is going to be f of 1, the y value when x equals 1. So I do 2 times f of 1. And then I'm going to add to that a base of 2 times the height, which when x equals 3 is going to be f of 3. So 2 times f of 3. And remember that when we're doing f of 1 and f of 3, you're just substituting those numbers back into this original function way up here. This f of x equals -1/2 x squared plus 8. That's how you're getting those y values. You're substituting the x's in, and then once you do that, you should get let's see, looks like 22. Just for sake of time, I'm not going to switch back over to my calculator to punch that in. But if you do punch it in, you should end up with 22.
Melanie.
Yeah.
And a quick question about the last free response question you were going over.
Okay.
Can you touch on a little bit how students cannot assume that a function is increasing or decreasing based specifically on the table values unless it is explicitly told to you in the stem of the problem?
Okay, let me get back over there. Okay, so we're wanting to look at, so we're talking about part B. Say that again,
I think
Aaron, I'm sorry.
On the values of the table, unless it tells us that the function is decreasing, we can't just assume based on.
True, that's true. Because we don't know if it's going, you know, from between 0 and 2 at 1, it could possibly jump up to 60 and go back down to 14.4. Is that what you're asking me about?
Yeah, I think that if we were just given a blank table like that, we couldn't make that assumption, but because it states that in the problem, that's how we know we can proceed.
Yes, thank you. Thank you for saying that. That's true. We can't say that unless it tells us explicitly. Okay, any other questions about that? Okay. All right, let me get back to.
We had one more question, actually.
Okay.
From Emily. She wants to know for part B, could you use overestimate or underestimate instead of increasing and decreasing and still earn the points?
So you would have to say increasing and decreasing to get that point. The part B, I don't believe I mentioned this, but part B was only 1 point. But to get that point, you did have to actually say both overestimate and decreasing, because the overestimate you're picking, overestimate is your answer, you're picking which one it is, but the increasing decreasing part is your justification. So that's, to get that point, you have to state both. You have to declare whether it's an overestimate or an underestimate, and then you must also justify that by telling that F, or in this case, A of H is either increasing or decreasing. And in this case, it was decreasing.
Can I jump in too on that one?
Sure.
Yeah, and the only reason you didn't have to write if it was a left or right is because it was given in the problem.
Yes.
But it does take both of those things. It's got to be left or right, increasing or decreasing. But if they tell you which it's doing, you don't have to write it. I write it anyway just to be safe.
Okay. Any other questions about that free response before we move on?
That's a really good question. Thanks for asking that.
Yes, thank you so much. All right, so let's go back to our skill builder and let's look at the trapezoids. So with the trapezoids, we have n equal 4 again. Oh, looks like my screen's not catching up to me. Hang tight just a second. Let me try to reshare this with you. There we go. I think we're back. Okay, so with the trapezoids, you want to use n equal 4, so 4 subintervals. So again, our base is going to be 1. Now, when I used to do this where I would switch my delta, my tangent, my x's, and call those my heights and relate it back to our geometry formula for area of a trapezoid. But I think if you'll remember, if you'll think of it this way, that to find the area of the trapezoid, think about it as averaging your heights and then multiply that times your base. Since we're already thinking about the delta x's as our base, this is just another way to think about that trapezoid formula for finding the area. So let me show you what I mean by that. When I build my trapezoid, my first trapezoid, I'm going to have a height when x equals 0 and a height when x equals 1. And I'm going to build a trapezoid using those 2 points, the height, and then the base of 1. Now, technically, whenever you're doing the area of a trapezoid, in geometry, you most likely learn the formula 1/2 b1 plus b2 times h, and we're still using that formula. But if you think about it as the average of the heights, since we were already talking about those y value as heights, and then the base is the change in the x values, it just sort of goes along with what we've been doing with the Riemann sums a little more smoothly, I think. You can also think about this trapezoid, kind of turn it on its side, and it looks like a traditional trapezoid that you studied in geometry. And you can think about this measurement here, the delta x measurement, the change in x measurement as the height. That's another way to think of it. But again, I think it makes it really easy if you just relate it to what we've already been doing and take the average of your heights. So add the heights together, the y values together, divide that by 2, and then multiply that times the base. Then let's go ahead and construct our other trapezoids. So we've got one here. We need 4 of them. And we've got this one. And then we've got one here. This last one is a triangle. Excuse me. Okay. So now we're going to find, again, we're approximating the area under the curve. So we're doing the integral from 0 to 4. We're still using f of x. And so to find the area of that first trapezoid, if you'll take f of 0 and f of 1 and average them, those are the heights. Or if you're thinking about it as base 1 and base 2, those are the bases. So you're going to average those, and you're going to multiply that times our 1. Then we're going to add to that this f of 1 plus f of 2, and we're averaging it, so we're dividing it by 2, times the base of 1. And then we're going to add 2, f of 2, and f of 3 averaged times the 1. And then the f of 3 and the f of 4. Average times the base. So one thing that I will point out before we figure out what the answer to this one is, notice that each of the f of 1, f of 2, and f of 3, they each, and then the f of 0, the endpoints are only used once. And that comes into play whenever we're doing the free response item involving a table. So I just want to point that out here with this illustration. Now, if you do punch that into your calculator, you should come up with 21. So if you're watching this on the replay, you know, you can pause it here for a minute, make sure you're punching in your calculator, and then just compare your answers as you're going through. Make sure you're actually doing some of the computation so that you know how to punch it in your calculator correctly. I did mention earlier that we could have left a numerical answer, but I want to, if you're using this notation like I am, I think you should go ahead and, you know, you're going to figure out what either the answer is, or you're going to actually show those substitutions. All right, so I'm going back to the other file, and I want us to fill in our justification sheet for the trapezoidal sums. So sometimes if you're doing a trapezoidal sum on the free response item, then you're going to be asked whether or not it's an over and under estimate. And that's all dependent upon the concavity of the function. So you could see on that last graph, remember when we're talking about concavity, we have concave up versus concave down. And the last function was more concave down. Well, it was concave down. And so if your function is concave down, then your trapezoid rule is going to be an underestimate. That was the example that we just completed. Concave down is an underestimate, so let's jot that in here when f of x is concave down. And then for the overestimate is when f of x is concave up. That's what you would use for your justification. That's what you're going to use for your reason. And when you're asked that on the AP exam, again, I want to make sure to say that not only do you have to pick under or overestimate, you do have to justify it. And this is how you would justify it with a trapezoidal sum based off of the concavity. I should also mention that you know that f of x is concave down when f double prime is negative and concave up when f prime is positive. So that might be something that helps you determine your reasoning. Along with up here on left and right Riemann sums, we know that when f of x is decreasing, that means f prime is negative. So that might be something that helps you justify just based off what information you're given in the problem. Same packet, if you'll look now at the 2019 free response item. Number 2B. Number 2B, we're looking at the velocity of a particle P moving along the x-axis as given by the differentiable function V sub P of T. It's measured in meters per hour and T is measured in hours. Selected values of V sub P of T are shown in the table above. Particle P is at the origin at time T equals 0. So part B for that particular year asked us to use a trapezoid, well, that was just last year, use a trapezoidal sum with 3 subintervals to approximate the value from 0 to 2.8 of V sub P of T. So be careful on this one because notice how the integral that we're looking at, the definite integral upper bound is 2.8. So we're not actually going to use this last column in the table over here. Well, at least not for this part. We're only looking at 3 subintervals, and those subintervals, again, are 0 to 0.3, 0.3 to 1.7, and then 1.7 to 2.8. So we're going to ignore that last column for this particular part. So now, again, if you think about the change in your x's as your base, that's going to be 0.3. And then we're going to use the average of our heights. So we're going to say this is equal to 0 plus 55 over 2 times 0.3. So you do your change in your x's. That's for your base, and then you average your heights, which is 0 plus 55 over 2. Then we're going to do the change from 0.3 to 1.7. That's going to give us 1.4. And our heights here are going to be 55 and negative 29. So we're going to add to that 55 plus a negative 29 over 2 times our 1.4. Then we'll add to that our third trapezoid. We're going from 1.7 to 2.8, so that's going to be 1.1. And then we're going to use the average of negative 29 and 55. Times the 1.1. And so you can leave it like that to get your full credit, or you could go ahead and, if you do get the actual answer to that one, it should be 40.75. And that was just worth 1 point. Okay, let's see. Aaron, would it be okay if we let them, the ones that are on, try one and drop their answer to us in the chat box, or do you want, would that take too much time, you think?
We have about 5 minutes remaining, so if that's how you want to close it out, that would be fine.
Okay, all right, so how about we look at this next response from 2016, and let's give you guys a chance to try one on your own. And then if you want to drop it in the chat box to me privately, you can, or there's a way you can respond to everyone or to me or to Aaron or however you want to do it. But we'll give you a few minutes to look at this one. It says the water is pumped into a tank at a rate modeled by W of T, for T is in between 0 and 8, where T is measured in hours. Water is removed from the tank at a rate modeled by R of T liters per hour, where R is differentiable and decreasing from 0 to 8. Selected values of R of T are shown in the table above. At time t equals 0, there are 50,000 liters of water in the tank. So a lot of information here in the stem, but we are looking specifically at number 1B, which is asking us to use a left Riemann sum with 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. Then they do ask us if it's an overestimate or an underestimate, and then give a reason for your answer. So we'll give you a minute to try this one on your own. And if you feel comfortable, like I said, you can either drop it in the chat box to me privately, or you can share it with the group. I feel like we need some Jeopardy music playing in the background. Okay, I think you've had at least some time to get started. If you haven't come up with your answer, that's okay. Just to wrap this up, I'll go ahead and start working. So what you should be approximating, of course, is the integral from 0 to 8 of R of T, since R of T represents the rate at which the water is removed. So you can find that here. And then it's asking us for a left Riemann sum. So we're going to start on the left-hand side, and our base is going to be 1, and our height's going to be 1340. So we're going to do 1 times 1340. And we're going to add to that a base of 2 and a height of 1190. And then we'll add to that a base of 3 and a height of 950. And finally, we have a base of 2 and a height of 740. And so that gives us 8,050 liters. And the question is it an overestimate or an underestimate of the total amount of water removed? And so if anybody wants to, they can drop their guess in the chat box. Not their guess, their answer. But we have a left Riemann sum, and again, it tells us that R is decreasing. And so that means this is going to be an overestimate. So we're going to say, so an overestimate since R of t is decreasing.
Shout
All
out
right.
to Krista who got that correct. She
Oh,
messaged.
yay. Awesome. All right. I think I am out of time. Are we at 10, Aaron?
We are at 10.
All right. Well, thank you guys so much for joining us today. This was fun, calculus on this beautiful day. So hopefully you get out and enjoy the sunshine.
All right, so I'm going to share my screen here. Just a couple of reminders, announcements here. If you need to get in contact with us, all of our information is there on the screen. Very special thank you to Melanie for doing an outstanding job kicking us off on our online review sessions. Hopefully everybody that was in attendance found it useful. Again, the handouts, the KYAP 2020 website is listed there. Next week, tune in, same time. We'll be doing Unit 6, Part 2, which will focus on the fundamental theorem of calculus. Brock Strickland from Colorado will be our guest presenter. So please tune in, get the handouts ahead of time, have questions ready to go. Melanie, Michael, any other closing words?
Not for me. Thank you all for joining us.
All right, thank you
Good
very
job,
much.
Melanie.
Yeah, we will see you all next week, hopefully.
Bye-bye.